In this video, we're going to look at the next type of intermolecular force. So having already considered van der Waals between non-polar molecules, we're going to look at permanent dipole-dipole forces that occur between molecules which have a permanent dipole. So they have a polar bond and also they're asymmetrical, and so there is a slightly positive end to the molecule permanently there and a slightly negative. So unlike van der Waals, which is a temporary dipole occurrence, this is a permanent dipole. And these are going to add on top of van der Waals forces. So when we have this permanent dipole, we're going to say that we've got two atoms, like H and X. If X is more electronegative than H, there's a permanent dipole, and the next molecule can attract to this molecule. So the delta plus end of one molecule, so this is permanently there, this delta plus and delta minus, is attracted to the delta minus end of another molecule. So not the same molecule, another molecule, intermolecular. They're usually stronger than van der Waals forces because they're permanent and not temporary. But we do need to say if they are the same size, because size matters. So if we have a look at HCl. So in a HCl molecule, chlorine is more electronegative than hydrogen, so there is a permanent dipole across the molecule. Polar bond, permanent dipole. The next molecule, the delta plus end, is going to be attracted to the delta minus end of the first molecule. There's a weak force of attraction. We're going to call this our permanent dipole force. So it's like an attraction between, like magnets. Propanone is a molecule that we haven't come across yet, but if I show you that it looks like this, carbon-hydrogen is a non-polar bond, that's the hydrocarbon part, but oxygen is more electronegative than carbon. So if we line another one of these trigonal planar shapes up, we can see the delta plus end of one molecule being attracted to the delta minus end of another. That is the permanent dipole-dipole force. So substances with permanent dipole-dipole tend to have higher boiling points than those with van der Waals that have a similar size. We've got a question here. It says chlorine, which is Cl2, has a boiling point of 239 K, whereas HCl has a boiling point of 188 K. Now, chlorine is non-polar. So if we start off, chlorine is a non-polar molecule with van der Waals forces, because it's non-polar, has van der Waals forces between the molecules. HCl is polar because Cl is more electronegative than H, with permanent dipole-dipole forces between the molecules. Now, it would appear that we would expect HCl to have the higher boiling point, but Cl2 has the higher boiling point. So why does Cl2 have a higher boiling point, even though HCl has permanent dipole-dipole? You need to look at the size. So the MR of Cl2 is much bigger, so it's 2 chlorines at 35.5, whereas HCl is 35.5 plus 1, so 36.5. Cl2 is nearly twice the size of HCl. So Cl2 is much larger, so we can't compare two things if they're not the same size. So Cl2 is larger with more electrons. And from the boiling points, we can therefore deduce the van der Waals forces, and we're going to abbreviate that to the VDWs at this point. The VDWs, the van der Waals forces between Cl2 molecules are stronger than the permanent dipole-dipole forces between HCl molecules. It must be because of the boiling points. Permanent dipole-dipole forces between HCl molecules. So just bear in mind that size is important. Follow the information, follow the boiling points. What can you deduce?